Yep, okay. So in this first question, we have a question on transition metal. So define. So a lot of Cambridge question always start off with definition, whether it's the AS paper or A2 paper. So make sure you know your most basic thing on definitions, and these are all stated very clearly in the syllabus. And this is very stingy for 1 mark, but whether it's 1 mark or 2 marks, you gotta show similar kind of standard, right? So we know that a transition element forms ions or compounds. In fact, the compounds will contain the transition metal ions, in which the electronic configuration shows an incompletely filled d subshell. So the subshell is being filled with electrons. So if the electrons do not completely fill the d subshell, that means it's incompletely filled d subshell, you can consider that a transition element. I'll give you a very simple example. This is straight from AS. So for example, you have copper. Copper has a special configuration where you would expect it to be this, but in fact that does not happen. In fact, the repulsion when you pair them out in the 4s subshell is stronger, is more unfavorable compared to the repulsion when you pair them up in the 3D subshell. So instead, it forms 4s1 3d10. This is copper atom. Alright, so copper atom is on, well, when it forms ion, when you have copper plus 1, you will lose from the 4s before the 3d. That means you will get 3d10. So a lot of copper plus 1 salts are white. So their solution will be colorless. The copper plus 1 salts itself are white, just like all the main group salts like sodium salt, potassium salt, ammonium salt, because, well, you see, their D subshell is not incompletely filled. In fact, it's completely filled D subshell. So you do not consider copper as a transition metal, not when it's copper plus. Well, you consider copper as a transition metal when it forms Cu2 plus, but when it forms Cu plus, fully filled D subshell doesn't have that characteristic properties of colored compounds for transition metal. Okay, so these are not being asked here, but I thought it would be quite interesting to actually recap AS, not A2, AS electronic configuration, and to talk about the different oxidation state of copper in A2 as well, and also in AS.
Next bit, cadmium form 2 ions. Why cadmium is not a transition element? So this is the kind of what we call a negative definition. Okay, so you need to start off by thinking what is the definition of a transition element. Okay, once you get the what is a transition element, transition element is defined as it can form one or more ions that have an incompletely filled D subshell, right? Okay, so cadmium form 2 ions, all right, both of which the D orbitals are completely filled. So cadmium and its ions. So cadmium and its ions, maybe I should use cadmium. Cadmium forms the 2 ions that have completely filled 4D subshell, therefore not a transition element. So a transition element form ions, one or more ions that have incompletely filled D subshell. Yeah, okay. I use it in the context of this. There are 2 ions. I use it in the context of the 4D because of the particular example of cadmium, and I talk about the negative definition. So I talk about the positive definition and why it defied or why it goes against the positive definition. Therefore, it is not a transition element. Next bit, they want the total unpaired electrons in the D and the 4s. So you gotta read carefully, yeah. Each isolated atom. Okay, so you gotta write the configuration. I don't care about the fully filled inner shell, so I can do not krypton, I can do argon. Okay, and then there will be 4s. You would think it's 4s2 3d4, but you know, for chromium you prefer the half shell stability because here they will repel more than if they are unpaired as 5 electrons in the d subshell. So essentially you actually get, for chromium atom, is 4s1 3d5. Okay, so for manganese there is no such issue, so it's 4s2 3d5, and then for iron is argon 4s2 3d6, unpaired, right? Okay, so these are paired, so these two are paired electrons. Okay, so 4s1 is going to look like that. Oops, no. So there's the 4s, and then you have the 3d, so 1 2 3 4 5. So for the 3d, your number of unpaired electrons is going to be 5. Carefully, yeah, this is 3d. So this is the 3d with the 5 subshells. Yeah, the 4 is going to be 1. The manganese is just going to be 3d5, so it's just going to look like that, but the 4s is completely filled, so it's 0 and 5. For the iron, again, the 4s is completely filled, but the d6, you need to be careful, it's not 6 unpaired electron. Yeah, d6 means 1 2 3 4 5 6. So how many unpaired electrons do you have? You have 1 2 3 and 4. Alright, so you actually have 4 unpaired electrons. Okay, next bit, identifying the type of orbital. So this is a D, this is a S, this is a P. Okay, if you want to be specific, this is PZ because it cuts through the Z. Okay, this is just S, it's spherical. Okay, this thing cuts through the, so Z is in that plane, so this thing cuts in between X and Y, so it doesn't cut the axis, so this is actually dx square y square. Okay, but D would have been perfectly fine. So in this question, they want you to sketch the shape of a d orbitals. You can choose to draw any one of dxy, dyz, dxz, or you can draw dx square y square or dz square, whichever one you like. I'm just going to draw for one of them. I'm going to draw the one where it cuts the axis, where it cuts the x and the y axis. This is the dx square y square. Sorry, that is not the dx square y square. This is the, no, it is the dx square y square. Sorry, yeah, okay, cool. So can label it as well just to specify it.
Question 6, we need to draw the shape. We need to draw one of the 5 d orbitals. So you have dxy, dyz, dxz. You also have dx square y square, dz square as well. So whichever one you like to draw, just know that this one is cut through space, this one is cut through axis, and I'll probably draw the one which cut through the axis because they are nice and easy to draw. So if I had x and y, so the drawing the axis is very important because that's essentially dx square y square. When I say cut through axis, they cut through the axis. Okay, so dz square actually looks like this. So if there is x and y, actually doesn't matter, I can draw dz like this because I labeled this as z, and then I will have cut through the z-axis, and then I have like a cone in between, so there's dz square. The xy, yz, and xz, they don't cut through the axis, they cut through the space, and you should have learned all of this as part of your transition metal chemistry. In terms of electronic configuration, so I have nickel, so this is up to argon configurations. Once you're at argon, then you will feel potassium and calcium, which is 4s2, then you will feel up to 3d8. Okay, so nickel is what you say is group 10. This is Arabic numeral that appears at the very top of that particular group 10, because 2 plus 8, 10. All right, so for the nickel 3 plus, so lost 3 electrons, you fill 4s before 3d, but you also lose from 4s before 3d. So you need to lose 3 electrons. So lose 2 and then lose another one. So you have 3d7. So be careful. Just because a lot of time we see nickel 2 plus does not mean they always ask a nickel 2 plus. So you need to read question very carefully. Moving on to question 2. So the one for the atom itself. So the thing about copper is that, in fact, the thing about transition metal is you fill 4s before 3d, but you lose 4s before 3d. Okay, and then copper is one of those where if you look at the periodic table, you would think like it is argon, and then you would think it's 4s2, which is potassium, calcium, and then you will have like 3d9. But the problem with 3d9 versus 4s2 is this 4s2, the electrons, both the electrons are in the 4s subshell, they will repel more compared to if they are fully filled in the, they repel more in the 4s compared to pairing them up in the 3d. So meaning to say, you don't get that, but instead you get 4s1 and 3d10. Like that. So the paired electron here, instead of 3d9, the pairing the electrons in the 3d, it is more favorable than pairing the electrons in the 4s. That's why I prefer to adopt that configuration and not this. Okay, these are either the half shell stability for the electronic configuration of chromium, okay, or you can talk about the full shell stability compared to the paired electron repulsion in the 4s for copper. So now because it's copper 2 plus, I lose 2 electrons. I lose the first one from 4s because there's only one there, and I lose the second one from the 3d. So there's nothing in the 4s, and I'm left with just 9 in the 3d because I lose the first one there and I lose the second one there. Okay. Save me like 10 minutes, I would say. Although you don't get to skip questions and exams, yeah, you need to come back to it if you want to earn your maximum mark. For transition metal electronic configuration, so go to your periodic table. I hope you can see cobalt is, you fill argon, and then you go to potassium and calcium, that's 4s2, and then you go to the 3d, scandium is 3d1, titanium 3d2, blah 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 blah. You go to cobalt, that's 3d7. Okay, so we know that cobalt doesn't have that half shell stability thing that you will get with copper or chromium. So cobalt is just normal, but they want you to write in full, not in terms of argon configuration. That's easily done. That is your argon configuration. There's 18 electrons there. Then it's 4s2 3d7, that's atom. You lose 2 electrons. You fill 4s before 3d, but you lose from 4s before 3d as well. Okay, so it's just 3d7 because you lose 2 electrons from the 4s. To start with, they want the electronic configuration of copper 2 ions. So it's important that we start from the copper atom. So if you have copper atom, you have 1s2, 2s2, 2p6, 3s2, 3p6. So that is essentially the configuration of argon. Then straight after argon, you move on to period 4, which is 4s2. Then you fill in potassium and calcium, and then you start filling in the d orbitals. Then this will give you 3d9. However, you also know that the configuration of copper prefer 4s1. So it prefer 4s1, 3d10 as a result of having an unpaired electron in the 4s orbital. So that will lead to lesser repulsion between the paired electrons, which you know it repel more than unpaired electron, right? Whereas for the d subshell, when the electrons are being paired in the d subshell, they repel lesser than being paired in the s subshell. So that's why we prefer this configuration for copper atom. We fill the 4s before the 3d, but when we remove the electrons to form the ion, we also remove from 4s before 3d. So you remove the first one from there, because there's the 4s1. Then you remove the second one from there, which means you're going to be left with, you continue that, so it's going to be 3p6, and then 3d9.
Okay, so that copper 2 configuration is a case study for you as well in A2 chemistry.